Hey guys, welcome to 15251's recitation video about a maximally cyclic group. Before you watch this video, I highly recommend that you check out the Diderot notes about modular arithmetic and group theory. I think that this question is a little bit involved and it might be helpful if you're already familiar with the definitions before we dive into this. Okay, that said, let's get started now. The question is this. Let's assume that you have two primes, p and q, such that q happens to be 2p plus 1. And now let's say that you have a subset of z star q, which we'll call h, that consists of the quadratic residues mod q. So a quadratic residue is really just some result of squaring a number and taking that result square mod q. So here we have the star. Next to the star, we have like the formal mathematical definition of h. It's a squared, where a ranges in z star q. Quick note, I'm going to sometimes talk about h as being a set, and sometimes I'm going to be talking about h as a group. I will conflate the two, but hopefully that doesn't cause too much confusion. So there's three things that we're going to prove. The first thing is that h is a subgroup of z star q. This less than or equal to symbol denotes subgroup usually. The second thing is that the order of h is equal to p. Recall that the definition of the order of a finite group is the number of elements in that group. And the third thing that we're going to prove is that for all elements of h that aren't the identity element, that element generates h. So what does it mean for an element to be a generator of h? Well, you are a generator if you can take powers of yourself and eventually see all the elements of the entire group. So h to the k for k in the naturals is equal to h. Sorry, I should have differentiated between little and big H. I'll try to do so in the future. Cool. So let's try and prove these three things. We'll start with number one, showing 1. So we want to show that H is a subgroup of Z star Q. So to do so, we'll use something called the subgroup test. We'll use the subgroup test. So there's three conditions for the subgroup test. The first is that we need to show that the underlying set of H is a subset of the underlying set of Z star Q. This is pretty clear, so I won't actually prove this. The second thing we need to show is something called closure of the group operation in H. Now recall that the group operation here is multiplication mod Q. So let's do this. Let a squared and b squared be arbitrary elements of H, where a and b are elements of Z star Q. So these are arbitrary elements of H. We want to show that a squared b squared is also in H. So what is a squared b squared? A squared b squared is equal to a times b times b, where recall that this multiplication, this operation here is just multiplication mod q. Now, multiplication mod q is commutative, so I can flip these two things. And I can say that this is a times b times a times b. Now recall, by definition, a group's, the underlying operation in a group should also be associative, right? Which means that I can stick parentheses, boys, like so, right? So what I've proven here is that a squared b squared is actually equal to ab fully squared. Cool. And note that ab is definitely going to be an element of Z star Q. So we have that a squared b squared is some element of Z star Q squared. Cool. So we do have closure. The third and final thing that we need to prove in order to show that H is a subgroup is that every element in H has an inverse. Cool. So let a squared be an arbitrary element of H, where a in Z star Q is arbitrary. Cool. We want to show that a squared inverse in H exists. So observe the following. We know that a inverse in Z star Q exists, right? since Z star Q is a group, it should have inverses. So we know that A inverse in Z star Q exists. This tells us that A inverse squared should be an element of H, right? Cool. And notice that A inverse squared is equal to A squared inverse. So cool, we've managed to prove the three things that we needed to prove in order to show that H is a subgroup of Z star Q. Now the second thing that we wanted to prove is we want to show that the order of H, or the size of the underlying set, is equal to P. So we're going to do this in two steps. 2.1, we'll show that the size of H, or the order of H, is at most P, and in 2.2, we'll show that the size of H is at least P. Cool. And these two things together would show that the order of H is equal to P. Cool. So let's start by showing 2.1. The size of H is less than or equal to P. Let's start by showing this. Okay, so recall that H was defined to be the set of quadratic residues mod Q. A squared such that A ranges over Z star Q, right? And recall that Q is equal to 2P plus 1, right? So this is what H was defined to be. Now we can make the claim, this equality here is going to be a claim, that this is actually the same set as A squared, but ranging over just 1 to P. Now, why is this true? The reason this is true is because for any A in Z star Q, we have that A squared is going to be congruent to Q minus A fully squared mod Q. Okay, so maybe it's not immediately clear why this makes these two sets equal, the two sets that I've claimed to be equal, why they're actually equal. So maybe let's look at an example, right? So an example is we can think about P being 3 and maybe Q being 7. Now the claim that I'm making is that the following two sets are the same. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Notice I'm not actually saying squared. These are actually just like squared mod Q. Or squared mod 7, I'm claiming that these two sets are equal. And the reason that they're equal is because 1 squared is actually the same thing as 6 squared, 2 squared is the same thing as 5 squared, and 3 squared is the same thing as 4 squared, right? So these two sets are equal for this reason. Cool. So now I've shown that H is really just equal to A squared for 1 is less than or equal to A is less than or equal to P, right? So this shows that H has at most P elements in it, right? Because sure, I know that H is the result of 1 squared to P squared, but how do I know that like 3 squared isn't the same thing as like 5 squared, right? How do I know necessarily that like all of these different things, all of the results of squaring things from 1 to P are actually distinct results, distinct residues, if you will. Right, that's the next thing that we have to show. Right, so we've upper bounded the order of H with P. Now we want to equivalently lower bound the order of H with P as well. So now we're going to show that the order of H, right, is at least P. Right, maybe I should have written 2.2. Oh well, this is not very aesthetic. Cool, we're going to show that the order of H is at least P, right? So how? We'll provide an injection F from the set 1 to P to H. Okay, we're going to provide an injection from the set 1 to P to H, right? This shows that P equal to the size of this domain, right, is less than or equal to the order of H. Cool, so let's provide this injection. F will take some number A, right, from 1 to P, and it'll spit out A squared mod Q. Cool. So proof of injectivity. let A and B be arbitrary elements of 1 to P. Cool. And assume that f of A is equal to f of B. So what does this mean? This means that A squared is equal to B squared. Cool. So we can subtract and say A squared minus B squared is equal to 0. And note that like equality means congruence mod Q. A squared minus B squared is equal to 0. And this is the same thing as A plus B times A minus B is equal to 0. Cool. Now we can throw this on either side, A plus B inverse. A plus B inverse times 0, right? And we can notice that this cancels out and gives us an E. So basically what we have here is A minus B is equal to 0, which gives us this A is equal to B. So what do we have? We've shown that f of A equals f of B implies A is equal to B. Okay, that's cool. Hold up, but not so fast though, right? Because I think we did make one step here that's not that obvious, specifically this step, right? So assuming this proof like completely works, that's great. We've shown that the order of H is at least P, which means that the order of H must now be exactly equal to P. But why does A plus B inverse necessarily exist? Right? So we need to like kind of justify why A plus B inverse really exists, why like this starred line actually makes sense mathematically. So notice that it suffices to show that A plus B is an element of Z star Q because all elements of Z star Q must have inverses since Z star Q is a group, right? This implies that like A plus B inverse in Z star Q exists. Cool, so let's try and prove that A plus B in Z star Q is actually in Z star Q, right? So notice that 1 is less than or equal to A, B is less than or equal to Q, which is equal to, less than or equal to P, right? This implies that 1 is less than A plus B, which is less than Q, right? So we have that A plus B is an element of 1 to Q minus 1. Well, actually 2 to Q minus 1, but specifically, A plus B is actually in Z star Q, which means that A plus B must have an inverse. Cool, so we didn't do anything jank here, is basically what I'm getting at. So congrats, we've now shown that the order of H is indeed P. Awesome. So now let's try and prove this third thing. For all H, that's not for all like elements of H that are not the identity, that element of H generates the entire group. So we're showing the third bullet point now. For all little h and h, h is not equal to the identity implies that little h is a generator of big H. Cool. Before we start this, I need you guys to recall two things. The first thing is that the only element of order 1 in any group is the unique identity element, right? And the second thing I need you guys to recall is order theorem. So what is order theorem? Let G be a group and let little g be an element of this group. And sorry, let's say let G be a finite group. Cool. So the order of G divides the order of the big group G. Okay, so this symbol here means divides, as in like 3 divides 9. Cool. And now what does it mean, the order of the little element G? So the order of little g is defined to be the minimum k in the positive naturals such that g to the k is equal to the identity element e. Cool. Now, let's prove a little lemma. This lemma is this, right? If the order of g is equal to the order of the entire group, then g generates g. G is a generator. I'm saying G a lot. Little g is a generator for big G, right? So why is this true? Let n equal the order of big G, right? And let n also equal the order of little g, right? This means if I look at the elements G1, G2, all the way up to G little n, right? This is the first element that was ever the identity, right? So what I want to claim is that these are n distinct elements of the group big G. So now assume for sake of contradiction that there exists some I and j that are not equal, and specifically without loss of generality, we'll say that I is the smaller one. Assume that I is less than or equal to j, and I don't know, I guess I'll also say that like I and j are in 1 to n, and it's true that g to the I is equal to g to the j. So basically I'm trying to like assume for sake of contradiction that two of these elements from g to the 1 all the way to g to the n are not distinct, they're equal, right? Then what would this mean? This would imply that g to the I times g to the I inverse is equal to g to the j times g to the j inverse, g to the I inverse, sorry. Cool. So this means that the identity element is equal to g to the j minus I, right? But that's weird because j minus I is strictly positive and j minus I is less than n, which is what we claimed the order of little g was, right? Remember that the order of little g was supposed to be the smallest positive exponent that you could raise little g to and get the identity. So we have a contradiction, right? So if we prove that the order of an element is the same as the order of its group, then it's necessarily a generator. Cool. So now we have all of the pieces to this puzzle, right? Let's let H be an element of the group H, right? And assume that H is not equal to the identity, right? So we know that the order of little h is either 1 or p, right? Because those are the only like things that divide p, right? 1 or p. We know that the order of h is equal to p because h is not equal to the identity element, right? So now we have that the order of h equals p, which is equal to the order of the group h. And this implies that little h generates h, or that h to the 1, h2, h3, dot, 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 h to the p is equal to h. Cool. And this property of a group having a generator like little h means that this group here is cyclic. Awesome. If there are any questions, please feel free to post them on Ditero. Otherwise, I hope to see you at live recitation too. Cool. Hope that helped. Thanks, guys.